All right. So, we were talking of the peak in scattering cross section in an NP scattering when you have angles much greater than 90 degrees, around say 180 degrees. So, a backward peak. Now, the kind of energies that were used in this in that experiment will suggest that the scattering or the deflection of the particles should be hardly few degrees. So, forward peak is or close to 0 degree peak is well expected, but a peak of around 180 degrees total back scattering, that is difficult to understand. And as we discussed, the explanation is much easier and elegant if we assume that the particles interchange their nature. So, if center of mass frame, if this is neutron and this is proton, and the because of scattering it goes in this direction, and because of scattering it goes in this direction. So, only a small deflection in the path. But then if this p during the interaction, if this becomes n neutron, so you get neutron this side, and this neutron during the interaction is if this becomes proton, then you see proton this side, and it will appear to the experimentalist as if the scattering is through very large angles around 180 degrees. If protons are going this way, protons are coming this way. If neutrons are going this way, neutrons are going returning this way. Now, this kind of exchange of neutron and proton, the character of the particle is possible if you take the exchange particle charged exchange particles into consideration. So, from here one can talk of the basic nature of forces, interactions, which is in quantum theory mediated by quantized particles, and from there one can reach or one can understand this kind of conversions. So, the most familiar case that you have is electromagnetic interactions, and you remember in the school days we say that if there is a charge q1 and if there is a charge q2, then q1 exerts a force on q2. So, this is our say first introduction or first level description. Where we say that q1 exerts on a force on q2, q2 exerts a force on q1, and the force, the magnitude of the force is q1 q2 by 4 pi epsilon naught r square and so on. But then as our understanding of nature increases, our tools are more sharpened, we say that no, this action at a distance picture is not good. It is not consistent with many of the established theories and other things. So, that second level thing comes where we introduce field, classical field. So, that is our next level, right, second level, next level description, classical fields. We say that q1 creates a field and field exerts force on q2. Okay. So, q1 creates a field. So, you make it a two step process. q1 creates a field and then q2 is placed in that field, that is why it experiences force. So, the interaction is through this field, it is not a direct interaction, interaction is through this field. So, that is the next level of understanding, and here this classical field is continuous and all those things. And then even further when you go next level, so this is electrodynamics. When you talk in terms of fields, classical fields, that is classical electrodynamics. And next level, when you bring in that quantum nature into picture and you talk of quantum electrodynamics, then you say that this field is not continuous, it has to be quantized, the field has to be quantized, any energy transfer has to be in units of certain minimum package. So, that quantization field is talked in terms of the quantized units, and there comes photons. Right, the field is described in terms of these quantized photons, and the interaction between Q1 and Q2 is through exchange of what we call virtual photons. So, the interaction is in terms of exchange of photons. So, these photons are the mediators of this electromagnetic interactions. You say that Q1 emits photons and those photons are absorbed by Q2, Q2 emits photons, those photons are absorbed by Q1, and these photons which are used in this interaction, they are called virtual photons, in the sense that they are not experimentally observable. Right. We do not observe those photons as we observe the photons coming from this tube light. The light is coming from this bulb and we can observe that light, we can measure the intensity, we can calculate the number of photons and all those things. These photons exist for a very, very short time, and we do not observe them, they only take part in this interactions. Now, if we do the same thing to our nucleon-nucleon interactions. So, we have a nucleon, call it N1, I have a nucleon, call it N2, just like you had Q1 and Q2. So, you have two nucleons here, and the if the interaction is mediated by such virtual particles, then this N1 should emit some particle, that exchange particle, and this N2 should absorb that exchange particle. So, N2 absorbs that particle. So, that is how the interaction will go. Now, what kind of particle is this? Photon was no charge and no rest mass and so on. This particle can have charge, can have mass. Can have charge, if I remember our experiment, if neutron is to be converted into proton and proton is to be converted into neutron, that can happen only if this exchange particle has got charge, right. So, it can have charge. It can also have mass, because the mass is related to the range of interaction, because if you consider this type of model, this type of mechanism for the interaction, then crucially that energy uncertainty comes into picture. Okay. If a non-zero rest mass particle is emitted from a proton and this proton still remains proton, right, the proton still remains proton or becomes neutron, mass wise it is the same. So, if a particle exchange particle is virtual exchange particle is emitted and this nucleon still remains a nucleon. So, that means that extra energy has been created, which is the rest mass energy of that exchange particle. And similarly, if this particle gets absorbed into another nucleon and even after that the nucleon remains nucleon, 938 MeV remains 938 MeV. So, that means the energy of that virtual particle which is absorbed, it appears nowhere. So, apparently energy conservation is violated. First you have created a particle without taking energy from the nucleon. Nucleon is still nucleon, proton or neutron is still 938 MeV, and then you have created a particle, and then that energy, that mc square, that exchange particle rest mass energy, that got absorbed into another nucleon, and still its energy did not increase. So, it appears there is a energy uncertainty, and that is of this type, mass of, let me put this pi here, you know why I am putting pi here. This is the kind of uncertainties, but then the uncertainty principle is allows this, right. Uncertainty principle allows this. You can have this kind of situations where energy appears to have been created out of nothing, or energy appears to get lost in nothing. So, those kind of violations are allowed by the theory. This is not only allowed by the theory, that is a central theme of the theory. Okay. The quantum theory is one of the very central idea of quantum theory is this uncertainty principle. But then this is allowed provided this violation, this energy uncertainty lasts for a very short time delta t, which is related to this delta E through that famous relation delta E delta t is h cross or h, right. So, in that case this delta t should be h cross divided by delta E, h cross divided by m pi c square. So, these particles can be created or absorbed, and they should exist to mediate the interaction between these two nucleons only for a time which is given by a relation of this type. Okay. And therefore, the range, that means, if these two particles are this much far away, and if this exchange particle has to go from here to here, it should get emitted here and should get absorbed here, or should get emitted and should get absorbed here, the particle has to travel this length. And even if the speed of the particle is close to c, this range of interaction should be less than or of the order of c times delta t, cannot exceed this. Okay. If these particles are too far away, then the virtual particles emitted here will only be absorbed by the same particle. Those virtual particles will not reach there, because they can exist only for this much of time, because they are when they are created or they are getting absorbed, there is an uncertainty of this order in energy, and therefore, they can exist only for this much time. And so, if this distance between these two nucleons is more than c times delta t, this exchange mechanism will not give any force, any interaction between these two. So, the range is related to the mass. So, this is equal to h cross c divided by m pi c square. Right. From here you can find what should be the rest mass, because range is more or less known. Okay. It is around 1 or 2 femtometers, that is the range. So, if you put 2 femtometers for examples, then m pi c square is h cross c divided by 2 femtometers. And how much is h cross c? H cross c is something like 200 mega electron volt h cross c Fm. Hc you must be remembering 1240 1240 1240 EV/nm or MeV Fm, same. You call it electron volt nanometer or call it mega electron volt femtometer, is the same. So, the same 1240 comes divided by 2 pi. 2 pi is around 6.28 or so. So, it would be 200 MeV femtometer, 2 femtometer, so 100 MeV. So, this exchange particle should have mass something of this type, about 100 MeV per c square divided by MeV by c square is the mass unit, right. So, it should be around 100 MeV by c square. Compare it to the nucleon mass energy 938 MeV, right. So, proton or neutron, the rest mass energy is around 938, 939 MeV. So, this is a massive particle, this exchange particle is a massive particle. It is not small compared to the nucleon which is emitting it or which is absorbing it, 100 around 100 MeV. Now, these virtual particles are virtual in the sense that they exist only for a very short time and you are not able to observe them in real world. Otherwise, they are not imaginary as such. If a particle of certain property is used here, is created here and is absorbed here, such and such particle with those properties must exist, all with all conservation laws and everything with the same properties, right. Photons, we can observe the photons do exist, they have some properties. The virtual photons we do not observe, but the property of the virtual photon is same as the property of this photon. If this photon does not have charge, that photon also does not have charge. So, everything angular momentum, spin, everything. So, if photon exists, then only you can have virtual photons there. Okay. So, do we have this type of particles? These type of particles, and it turns out that yes, we do have, and those particles are pions, and there are 3 variety of them: pi plus, pi minus, and pi 0 neutral. Okay. 3 varieties of pions. These are the particles which are observed in laboratories, real particles, real pions which are created in atmosphere by those cosmic rays, which are also created in laboratories using nuclear accelerators and nuclear reactions. So, these particles do exist, and therefore, if they can exist with all quark anti-quark structure and all laws of physics followed by these particles, then you can have corresponding virtual pions. So, all these things are very well studied, and these have mass around 139.6 mega electron volt, rest mass energy, or mass is this divided by c square. This has slightly smaller mass, 135 MeV. So, they are the right kind of particles which can mediate forces between the nucleons, right. I must have told earlier, this force between nucleons is some kind of residual color force. Is the strong force, you have strong force, weak force, electromagnetic force and gravitational force. The strong force is where quarks are interacting with the exchange of gluons, and that is because of the color charge carried by the quarks. Just like electrical charge carried by the particles result in electromagnetic interaction, in electromagnetic forces. Similarly, the color charge existing on these quarks, that results in these strong forces, and each nucleon is color neutral, because nucleon is made with those colors, 3 quarks, and the total color is 0. So, just like 2 atoms with 0 charge, each atom with 0 charge can combine to form molecule or can interact, right. Similarly, these nucleons which have 0 color here, 0 color here, but still if they are close enough, so that the distribution becomes important, then you have some forces. All right. So, so this is about pion exchange. Now, then you can have NP interaction. NP interaction can have all kinds of varieties. This can emit, what can it emit? This can emit a neutral pion. Right? N can emit a neutral virtual pion and still remain neutron, and this proton can absorb that and can still remain proton. And similarly, this proton can emit, this proton can emit neutral pion and still remain proton, and this neutron can absorb that pion and can still remain neutron. These are within that virtual processes. So, do not worry too much about the energy uncertainty and momentum uncertainty and all those things, because they are for that fleeting time. The time also you can estimate. If you estimate time from here, in fact, time you can estimate from this range itself. Time, we say that it is range divided by c, that is how we took it, right. And if the range is something like 2 femtometers and c is 3 into 10 to the power 8 meter per second. So, this is in seconds. So, this is 10 to the minus 23 seconds. So, the processes are for very small time. So, do not worry about how these reactions are energetically balanced and things like that. So, that is one. Yet another process is that N can emit what? Negative pion. The charge conservation should be there. So, N can emit a negative pion and convert itself into proton. The energy violation is similar. Neutron and proton have similar masses, and this pion has an extra mass. So, this is possible, and then P can, the other P, if this is N, this is P, this P can absorb this pi minus to become neutron, right. So, this proton becomes neutron, this neutron becomes proton if there is a pi minus exchange. And then proton can do a similar thing. Proton can convert itself into neutron by emitting pi plus, and this neutron can absorb that pi plus and become proton. So, there are three varieties of possibilities. You can have this NP interaction can be mediated by all three kinds of pions. It can be mediated by neutral pion, it can be mediated by negative pion, it can be mediated by positive pion. If you consider PP interaction between a proton and a proton, what kind of exchange particle can mediate this? Out of the three, pi 0, pi plus and pi minus, I am looking at interaction between two protons. So, what of these three, which pion or which pions can mediate this interaction between one proton and another proton? Like NP, one side neutron, other side proton, it was possible for the first particle to emit a neutral pion or a positive pion or a negative pion. All three could go there and get absorbed, right, these three equations, these three varieties. So, this NP interaction can be mediated by positive pion, can be mediated by negative pion, can be mediated by neutral pion. In that same spirit, if I have two protons sitting at some separation and I say that this emits a particular pion and that pion gets absorbed there, right. One proton emits a particular pion and the other proton absorbs it. What kind of pion that can be? Pi is yes, neutral pion. It has to be neutral pion, nothing else. Okay. P plus neutral pion, P emits a neutral pion and still remain P, and the other P absorbs that pion and still remains P. This is the only possibility. If this P emits a positive pion, that is possible, it can emit a positive pion and convert itself to N, but then this cannot be absorbed by the second, right. So, this cannot be absorbed, you do not have a particle of this nature, 2 units of charge or so on, you do not have a nucleon like that. So, this is not possible. Similarly, pi minus is not possible. So, PP scattering or PP interaction can only be mediated by this neutral pion, whereas NP interaction can be mediated by all 3 of them. There is a small difference in the when you analyze scattering data, NP data and PP data, NP scattering data and PP scattering data with same energy, similar energy and so on, remove all that Coulomb interaction effects. So, that you are only looking at the nuclear interactions between proton-proton and neutron-proton. So, if you compare these two, what is the strength of interaction or what is the strength with which it is scattering, those parameters are there to compare, scattering length and other things. So, if you compare how strong they are interacting, you find that when it comes to you compare this PP and this NP, there is a slight difference, very close to each other, but there is slight difference. And if you analyze this NN and PP, they are same, the strength of this and this are same, whereas that of NP is slightly different. People give credit for that difference or responsibility for that difference to this difference in mass, slight difference in mass of neutral pion and charged pions. These interactions can only go through neutral pions, whereas these interactions can go through the neutral as well as the all 3 contribute. So, slight difference comes from there. With this mechanism, the potentials are created. So, there are 2 approaches. The first, which we described for quite some time, was you have the experimental data, and from those data and with some arguments, you keep on constructing potentials with variable parameters, so many parameters, and adjust the value of the parameters, so that you match with the data. Start with square well potential. Why? What is the basis of starting with the square well potential? Why not harmonic potential? Why not some other kind of potential? But since this square well potential had parameters like depth and width, we could play with those numbers and we could adjust the numbers, so that the neutron binding energy resulted from that. That does not mean that the interaction is described by square well potential. So, this type of approach, where we just select some potential with so many parameters which we can play with, which we can vary, and then we fix the values of those parameters according to the data available, so that the numbers coming from here match with the experiments. That is known as phenomenological approach. The potentials constructed that way are called phenomenological potentials. Whereas, if you start with a mechanism that the interaction is generated in this particular way, and from that mechanism you come out with a potential that can also have certain adjustable parameters, but the shape of the potential is not arbitrary. The shape of the potential is coming from the mechanism that, or more basic mechanism that you are contemplating. Now, here is that kind of case where the interaction mechanism is first laid down, and from here theory is developed, models are developed to get to the potentials. So, Yukawa did it in the year of 1934, 1935, and then came out with potentials which we called Yukawa potentials, and or we call it one exchange, one pion exchange potentials. OPEP, one pion exchange potential. So, and the dominant part is e to the power mu r over r and many more things, but this is the r dependence is dominated by this. You have spin part, you have non-central part, those things are put, but the r dependent part comes out to be this exponentials. So, there is a justification of the shape, it is coming because of this one pion exchange. You have different branches or different zones of nuclear interactions. Here with this kind of energy of pions around 135, 140 mega electron volt, you will have certain range which will come out around how much 2 femtometer we took, then it was 100. So, little less than that. So, in this range, which you can say for nuclear range, this is almost near the end, this works well. But if you are looking at interactions at the separation of say 0.5 femtometers, 0.4 femtometers, like that, much smaller separations. So, other mesons which exist or other exchange particles which exist with much higher energies, those can come into picture. Pions are not the only exchange particles, you have omega meson and many other type of particles with higher energies. Since they have higher energies, that energy violation is larger, and therefore, the range C delta T that they can cover is smaller. So, they will not take part into interaction if the separation is say 1.5 femtometers or 1.7 femtometers, because their lifetime or their existence time, those higher mass particles, their existence time is so small, they can, let us say they can travel only a distance of 0.4 femtometer. So, these mesons will not contribute in the interaction if the two nucleons are at a separation of 1 femtometer or 2 femtometers or 1.5 femtometers. Okay. But if nucleons are pushed at that small separation 0.4 femtometer, 0.5 femtometer, 0.3 femtometers, then those mesons will also start interacting. So, that repulsive core, for example, we talked of repulsive core and all those things, that will not come from one pion exchange, that will come from those higher order particles. So, one can have 2 pion exchange, one can have omega meson exchange and varieties of those things. So, this is one approach where one starts with more basic mechanism and comes out with potentials, right, the nuclear potentials between 2 nucleons. So, that is all about that. Okay. So, this is about force or interaction between 2 nucleons. So, we talked about bound system of 2 nucleons, that gave us some information about the interaction. And we also talked about scattering between these two nucleons, pp scattering or np scattering and n scattering, but essentially it was two nucleons interacting with each other. Now, if I look at a nucleus, apart from this deuteron, all nuclei will have more than 2 nucleons, helium 4 nucleons, right. Similarly, iron 56 nucleons, all packed in that nuclear radius, nuclear volume. So, if we try to look at the interactions between all those nucleons which are there in the nucleus, that could be a very, very formidable task. With 2 nucleons, we had so much of discussions and so much to understand and so many experiments and so many theory and big expressions and non-central part and central part and spin dependence and exchange and this and that, just with 2 nucleons. Now, if there are 10 nucleons or 20 nucleons or 13 nucleons or 56 nucleons or 80 nucleons, and if we try to look at the net interaction and the total energy and all the properties, the magnetic moments or angular momentum and this and that, from the very basic nucleonic interactions, it could be a very, very difficult task. And yet another complication is that in a nucleus, you have so called many body forces coming into picture. That means, many body forces means, suppose you have 3 nucleons, suppose you have 3 nucleons, one here, one here, one here. This is named A, this is named B, this is named C. And you say that force on A, we do not talk in terms of force, we talk in some potentials, but anyway I am not going to do any mathematics, qualitative only. So, force on A is because of B and because of C. Normally this is how we think, right. On A, if A and B are there alone, B exerts force on A exerts force on B. If A and C are alone, existing alone, then C will exert force on A will exert force on C. If both of them are here, the net force on this A is force from B plus force from C. That is how we think, but in nucleus, apart from this, you have yet another term, which is some extra, something extra. If you have 3 nucleons together, then there is something extra. You can, if you wish, you can write is BC. This is 3 body force. This is 2 body force. This is 2 body force. So, there is a lot of calculations, lot of theory developed for these multi-body forces. It is not that since there are too many particles, I have too many pairs to consider for interaction. It is even more than that, even more than that. Those pairwise interactions will come under 2 body forces, but you have 3 body forces or maybe 4 body forces. Of course, relative importance will decrease. Most dominant will be 2 body forces and then 3 body and 4 body. So, that means, even if I know this nucleon-nucleon interaction potential very well, I will not be able to write the Hamiltonian for the entire interaction inside the nucleus, because those 3 body 4 body forces will also be present. So, that is yet another complication. Even this 2 body interactions, if you try to write for all pairs in the nucleus and solve that Hamiltonian, you understand how big it will be. Similar is the situation in atomic physics. Of course, that 3 body things are not relevant, not much significant there. The simplest was hydrogen or hydrogen like. where you only had one electron and one particle here Z e. And then its Hamiltonian in Ez, you write this just as minus h cross square by 2 m del square, and this potential energy between this and this, correct. So, it is minus Z e square over 4 pi epsilon naught r. But if you have a multi electron system, then the Hamiltonian will have for each electron you will write kinetic energy term, for each electron you will write potential energy with the nucleus, and on top of that you will also write the interaction energy between the electrons, among the electrons themselves. So, summation over I and summation over j, and I not equal to j, then it will be E square 4 pi epsilon naught mod of R I minus R j. So, the whole thing becomes very difficult to handle. So, how does atomic physicists deal with this situation? They say that this entire atom is producing some kind of an effective central potential for one electron to come. In the atom, if you have z electrons, say 20 electrons or 16 electrons, so that nucleus plus all this remaining electrons, although if you write the potential it will be a weird thing, but one assumes that all this is equivalent to a single central potential, and you do not have to consider the coordinates of this electron and coordinates of that electron and coordinates of that electron and what kind of potential they are producing for the one electron that I have in mind, which all these things are replaced by one single potential origin and some kind of V as a function of R, finish. This V as a function of R will not be this Coulombic expression, will be some equivalent of all these things. But once you have that central potential, then you solve just one equation, not this, equation like this. You consider one electron in this potential. This is that equivalent potential coming from all the remaining electrons and the nucleus and everything. So, that what formula or what expression is to be written, that is a separate story, but at the end of it, it is one single potential with one single coordinate coming in. And this electron, one electron that I have in mind, this is called single particle potential. So, that one particle, one electron I have in mind, that will be at this position R, and with this Hamiltonian you will solve Schrodinger equations to get the energy, possible energies of that electron, and that is valid for all the electrons of the atom, all the 16 electrons of the atom, for each one of them the same potential and same energy levels are available. Okay. So, when you do that, what happens? If it is a central potential and not Coulombic potential, you will have energy depending on two parameters, energy depending on n and energy depending on L, orbital angular momentum quantum number, principal quantum number, and then you will have energies like 1s, that is n equal to 0 and L is equal to n equal to 1 and L is equal to 0. So, that this is 1s, then you will have 2s, you will have 2p, right, n is equal to 2, L equal to 0, L equal to 1, 2p, then you will have 3s, you will have 3 p. Then the 4 s is somewhere here. In general 3d is slightly above, and then you have 4 p, and then you have 5 s, and so on. So, energies, different energy levels appear for different n and l, and it so happens that there are gaps in energy, bigger gaps. Here also there is a gap, but this is a smaller gap, here is a bigger gap, here is a bigger gap, here is a bigger gap. So, these are called shells, major shells. Now, this is one shell, this is another shell, this is another shell, this is another shell, and so on. And these are energy levels, they are not non-degenerate, they are degenerate energy level. One degeneracy comes from spin, because the central potential that we solve, that does not have spin in it. So, spin up, spin down, those energies will be same as long as this Hamiltonian is concerned. They may depend on the energy may really depend on spin, but then you have to bring in extra terms L dot S or something. So, the basic Hamiltonian allows spin degeneracy, and on top of that it will allow that L degeneracy, because with any given L, ML can be plus L, L minus 1, L minus 2 up to minus L. So, that degeneracy is also there. Energy does not depend on ML, it depends on L, energy depends on L, S and P, the energies are different. So, it depends on L, but it does not depend on ML. Therefore, at the same energy, if L is equal to 1, then ML equal to plus 1, ML equal to minus 1, ML equal to 0, they will appear at the same energy, and then spin up and spin down. So, the total number of quantum states will be 2 here, will be 2 here, will be 6 here, will be 2 here, will be 6 here, will be 2 here, will be 10 here, will be 6 here, and so on, right. And then if you look at those gaps and call them as shells, then this shell is at 2 and this shell is at 10. And cumulative I am writing. This shell itself contains 8 quantum levels, quantum states, add this 2 also. So, you have 10, and then this is one shell, this makes it 18, this is one shell and this makes it 36, and so on. Next will be 54 and so on. And these different shells with different energy, with larger gaps in between, that reflects in the periodicity of many of the properties of atoms. Okay. Much before all this was developed, the periodic table concept was there, because people had seen that periodicity in properties. So, and atomic weights, not atomic numbers, atomic weights they had determined for different elements, and therefore, in terms in increasing order of atomic weights they had tried before this atomic number came into picture. So, some kind of periodic table was evolving, and finally, now we know that it is all if it is arranged with this atomic number, very nice repetitive properties come in the groups, in the periods, and so on. So, that shell structure is now very well established. Now, look at your screen. On the screen you should see the picture. So, on this graph what I have shown is atomic number on this x axis, and you can see 0, 4, 8, 12 at this interval it is written the measure scale. On the y axis it is radius, atomic radius in picometers, and this graph has been created in Excel, very simple, and the vertical grid lines are added so that you can see it. Now, see here what happens. The atomic radius keeps decreasing, it is here, this is 3, this is lithium, this is Z is equal to 3 lithium, and then it decreases, this is Z is equal to 4, 5, 6 and so on, this is 8, okay. Next cell starts here, and then all of a sudden you see that the this radius has increased, and then again it decreases, and when the next measure shell starts, it increases, again it decreases, and it decreases, and then it goes, and here it increases again, right. The shell closes at different places, and there it really gets up. Here this is 37, shell closes at 36, and 37th, once you go to 37, you see that it has gone up. Similarly, here you can see it is at 19. So, shell closes at 18, and as you go for 19th, all of a sudden atomic radius increases. This sudden change in atomic radius is one indication that somewhere you are having those different shells. I will show one more thing. This is ionization energy. Ionization energy is the energy that is needed to remove one electron, this is first ionization energy, one electron from the atom. So, that is ionization energy, and here also you will see here the ionization energy is very high. That means, it is now difficult to remove that electron from the atom, but one more electron, next element here, all of a sudden ionization energy drops. So, a new shell has started with this addition of one electron, and therefore, it is so easy to take it out. So, ionization energy is much less. So, it is loosely bound. So, with very small energy you can take it out. So, but then it goes up, it goes up, it reaches here. This is 18, 18 is a shell closer. You can look at your board, 18 is a shell closer, the shell closes at 18. So, 18, if you have 18 electrons, then the ionization energy is quite high, but if you have 19 electrons, the ionization energy is all of a sudden drops. So, that shows the shell structure. Inside the shell, if you look at inside the shell, that means from here to here, it is slowly increasing, and when you change the shell, you are going from one shell to the other shell, 18 to 19, then it suddenly it goes down. Then after 18, the next shell closure is at 36. On the board you had seen that at 36. So, look at from 18 to 36, the ionization energy is slowly increasing or decreasing or slowly changing, but as you go from 36 to 37, all of sudden the energy ionization energy goes down, right. So, this kind of discrete changes, this kind of sudden jumps in various properties, they indicate that there is some kind of a shell structure, where one shell closes, the next shell starts, and then that next shell keeps filling, and once that shell is closed, then again next shell starts, and that change from the starting of a new shell, that is marked by sudden change in properties, right. All right. So, come to the board again. This is helium, Z is equal to 2 is helium, very tight atom, removing electron is not that easy, but once you go from helium to lithium, that third electron can just come out easily. And similarly, next will be the at 10 in the periodic table, 10, then 18, and then 36. These kind of different shells are there. And how do you make it? Just by saying that 2 electrons will come here, one with spin, one with spin down, and any third electron must go here. in that differential. Why this third electron cannot be accommodated here? This is because they are fermions. Electrons are fermions. No two fermions can occupy the same quantum state. That is why they have to go up. Now, similar structure exists in nuclei also. In nuclei also, what we can do? We can have an average kind of potential, one particle potential, single particle potential. There are so many nucleons in the nucleus. Think that this whole nucleus is presenting to any one single nucleus, the whole nucleon to any one single nucleon, this whole remaining nucleus is presenting this potential. Same for all nucleons. Solve this potential, get the energy levels, and then fill the energy, those quantum states from below, and remembering that protons and neutrons are also fermions. So, one quantum state can accommodate only one particle. So, all that Pauli exclusion principles, and then you come up with a similar shell structure. The first thing is, if there are this kind of interactions, that shell structure should be visible in experiments. For example, nuclear radii, you have seen on your screen atomic radii, how atomic radii change as number of electrons increases and you go from one shell to the next shell. Similarly, nuclear radii, if there is a shell structure inside the nucleus, then this nuclear radii should also have this kind of jumps, sudden jumps, or corresponding to ionization energy, here you will have neutron separation energy or proton separation energy, that should have this kind of sudden jumps at certain fixed numbers, right. So, next lecture we will look at the experimental, some of the experimental data, and see if those data also suggest a shell type of structure inside the nucleus. So, that similar atomic models, the methods of atomic models can be employed there also, and you will see that yes, they do exist, and based on that one develops what we call nuclear shell model. Okay.